What if the universe as we know it, every atom, every force, every physical law exists in a state of false stability? What if, like a boulder balanced precariously on a cliff edge, reality itself could suddenly collapse into a lower, more stable state? Physicists studying the fundamental forces of nature have discovered that the quantum vacuum, the very fabric of empty space, might not be in its lowest energy configuration. It could decay, and if it does, a bubble of destruction would expand at the speed of light, transforming all matter, rewriting the laws of physics, and erasing everything in its path. There would be no warning, no escape, no survivors. The universe as we know it would simply cease to exist, replaced by something utterly alien where the physics we depend on no longer operates. Tonight, we journey through evidence suggesting our entire existence might be metastable, temporary, unstable, and doomed to eventual catastrophic transformation. Before we begin, please like and subscribe to our channel and let us know in the comments below where in the world you're watching from. Prepare yourselves. We begin. To understand vacuum decay, we must first understand what physicists mean by vacuum. In everyday language, vacuum means empty space, nothing. But in quantum physics, the vacuum is far from empty. It seethes with activity, filled with quantum fields that permeate all of space, fluctuating and producing virtual particles that pop in and out of existence. Every fundamental force in nature, electromagnetism, the weak nuclear force, the strong nuclear force, and gravity, corresponds to a quantum field filling all of space. The electromagnetic field exists everywhere, even in the darkest void between galaxies. So do the fields for quarks, electrons, neutrinos, and the Higgs boson. These fields have values at every point in space, and the vacuum is simply the state where these fields settle to their lowest energy configuration. Or so we thought. In 1977, physicist Sidney Coleman at Harvard published a paper that would transform how physicists think about the stability of reality itself. Coleman was studying quantum field theory, the framework describing how particles and forces interact. He realized that what we call the vacuum state might not be the true lowest energy state at all. It could be a false vacuum, a metastable state that appears stable but could suddenly transition to a true vacuum state. Think of a ball in a bowl on a table. The ball sits at the bottom of the bowl, a local minimum of gravitational potential energy. It's stable there, not rolling anywhere. But there's an even lower energy state available. If the ball somehow gets over the rim of the bowl, it could roll off the table and fall to the floor. The floor represents the true vacuum, the true minimum. The bottom of the bowl is a false vacuum, stable only because there's an energy barrier preventing transition to the true minimum. Coleman showed that quantum fields could exist in exactly this kind of metastable state. The Higgs field, the field responsible for giving particles their mass, might be sitting in a false vacuum, appearing stable, but actually capable of suddenly tunneling through the energy barrier to a true vacuum state. And if this transition happened anywhere in the universe, the consequences would be apocalyptic. The transition would create a bubble of true vacuum expanding at the speed of light. Inside the bubble, the Higgs field would have a different value, changing the masses of all fundamental particles. Electrons, quarks, and other particles would suddenly have different masses, likely much different. Atoms as we know them couldn't exist. The chemical bonds holding molecules together would dissolve. Every structure in the universe, planets, stars, living beings, would disintegrate instantly as the bubble wall passed through. And there would be no warning. Because the bubble expands at light speed, we'd never see it coming. The destruction would arrive at the same moment we detected it. One instant you're alive, reading these words. The next instant, before your neurons can fire, before any signal can propagate, you and everything around you ceases to exist in any meaningful form, replaced by a soup of particles with unfamiliar properties in a universe operating under alien physics. For decades, vacuum decay remained a theoretical possibility, discussed in academic papers but lacking concrete connection to measurable reality. That changed in 2012 with one of the most celebrated scientific discoveries of the century, the detection of the Higgs boson at CERN's Large Hadron Collider. The Higgs boson is a fundamental particle, an excitation of the Higgs field that permeates all space. Its discovery confirmed a crucial piece of the standard model of particle physics and explained how particles acquire mass. But the Higgs boson's measured properties, specifically its mass of 125 billion electron volts, brought disturbing news about vacuum stability. Once physicists knew the Higgs boson's mass, they could calculate the shape of the Higgs potential, the energy curve that determines whether our vacuum is stable, metastable, or unstable. The Higgs field's current value sits somewhere on this landscape, and whether it's stable depends on whether there are deeper valleys it could roll into. The calculations required knowing not just the Higgs mass, but also the masses of other particles, particularly the top quark, the heaviest known fundamental particle. By 2012, both values were known precisely enough to map the Higgs potential with confidence, and the results were unsettling. In 2012, physicists Dario Butatso, Giuseppe Di Grassi, and colleagues published detailed calculations showing that with the measured Higgs mass of 125 GeV and the top quark mass of 173 GeV, our vacuum appears to be metastable. We're not in the deepest possible valley. We're in a false vacuum, separated from the true vacuum by an energy barrier. The calculations suggested that at energy scales around 10 to the 10 GeV, far beyond anything achievable in particle accelerators, but present in the early universe and perhaps in extreme astrophysical events, the Higgs field could tunnel through the barrier and cascade into the true vacuum. Our universe is like that ball in the bowl on the table, stable for now, but not ultimately stable. But here's what makes this particularly troubling. The calculations also showed we're right on the edge. The measured values place us in a narrow band between absolute stability and immediate instability. If the Higgs mass were just 2% lighter, or the top quark mass 2% heavier, our vacuum would be absolutely stable, never capable of decay. If the values were slightly different in the opposite direction, our vacuum would be catastrophically unstable, having already decayed in the early universe. Instead, we exist in this knife-edge regime of metastability. This seems like an extraordinary coincidence. Why would the universe's fundamental parameters place us precisely in this narrow window? Some physicists see this as evidence of fine-tuning requiring explanation, perhaps anthropic selection in a multiverse, or deeper principles we don't yet understand. Others see it as troubling for a different reason. Metastability means vacuum decay is possible. It might not happen for an unimaginably long time, Current estimates suggest the vacuum's half-life is vastly longer than the universe's current age, perhaps 10 to the 100 years or more. But possible means it could happen tomorrow, next year, next century. We can calculate probability, but we can't predict when. To understand how vacuum decay would begin, we need to explore quantum tunneling, one of the strangest phenomena in physics. In quantum mechanics, particles don't simply move from place to place along definite paths. They exist as probability waves that can tunnel through barriers that classical physics says are impossible to cross. Imagine rolling a ball toward a hill. Classically, if the ball doesn't have enough energy to roll over the hill, it stops and rolls back. But quantum mechanically, there's a small probability the ball could simply appear on the other side of the hill without ever having enough energy to go over it. It tunnels through the barrier. This isn't just theoretical. Quantum tunneling is observed constantly in nature. It's responsible for radioactive decay. Particles escape atomic nuclei by tunneling through the binding energy barrier. It's essential for nuclear fusion in stars. Protons tunnel through the electromagnetic repulsion barrier to fuse together. It's used in technology. Scanning tunneling microscopes and flash memory storage both exploit quantum tunneling. For the Higgs field, tunneling means that even though our false vacuum appears stable, there's a small but non-zero probability that somewhere, at some point in space, the field could spontaneously tunnel through the energy barrier to the true vacuum. This would happen randomly, unpredictably, creating a tiny bubble of true vacuum in a sea of false vacuum. Once formed, this bubble wouldn't remain small. The true vacuum has lower energy than the false vacuum, so there's energy released when the transition occurs, like water flowing downhill. This energy goes into the bubble wall, causing it to expand. And critically, nothing limits the expansion speed except the speed of light itself. The mathematics of bubble nucleation was worked out in detail by Sidney Coleman and colleagues in the late 1970s and early 1980s. They showed that the rate at which bubbles form depends exponentially on the height and width of the energy barrier separating false and true vacua. High, wide barriers make tunneling extremely rare. Lower, narrower barriers make it more common. For our universe's measured parameters, the barrier is high and wide. Good news for us. Coleman's calculations suggest that in any given region of space the size of our observable universe, the probability of a bubble forming in the next billion years is negligibly small. We're talking about probabilities like 10 to the 100 or smaller, numbers so tiny that they're effectively zero for any practical purpose. But here's the issue. The universe is vast and cosmic time is long. Our observable universe is just one tiny patch of what might be an infinite cosmos. If the universe is truly infinite, then no matter how improbable vacuum decay is per unit volume per unit time, it's happening somewhere, sometime. Infinity times any non-zero probability is infinity. Moreover, the probability isn't the same everywhere. In regions of extremely high energy, like the very early universe during inflation, or potentially inside black holes, or in hypothetical collisions of neutron stars, the energy density might be high enough to significantly increase tunneling probability. These could be weak points where vacuum decay is more likely to begin. Let's trace what would happen if a vacuum decay bubble formed. The scenario is simultaneously fascinating and terrifying, a step-by-step description of how reality itself would be erased. T equals 0 seconds. Somewhere in the universe, through pure quantum chance or triggered by some high-energy event, the Higgs field tunnels through the energy barrier. A bubble of true vacuum forms, initially microscopic, perhaps no larger than a proton. Inside this bubble, the Higgs field has a different value, maybe much lower than in our false vacuum, possibly even 0. T equals 10 to the power of minus 43 seconds, 1 Planck time. The bubble has already expanded at light speed to many times its original size. The boundary between true and false vacuum is a thin shell, the bubble wall, where the Higgs field transitions between values. This wall releases enormous energy as the field rolls down to its true minimum. The energy creates intense radiation and particle production. T equals 10 to the power of negative 10 seconds. The bubble is now centimeters across and growing relentlessly. Inside, the physics is alien. If the Higgs field's value is significantly different from our vacuum, particles have different masses. Electrons might be much heavier, making atoms impossible. Or quarks might have different masses, changing how they combine into protons and neutrons, perhaps preventing stable atomic nuclei from existing at all. T equals 1 second. The bubble is now 300,000 kilometers across, comparable to the distance from Earth to the Moon. Its wall is a sphere of destruction expanding in all directions. Nothing inside retains its original structure. Atoms have dissolved, molecules have ceased to exist. If there was life in the bubble's path, it was annihilated instantly, its atoms torn apart by the changed physical constants. T equals 1 hour. The bubble is 1 billion kilometers across, larger than the Sun. If it formed in our solar system, it would have already engulfed several planets. Each world would be destroyed in a fraction of a second as the wall passed through. The rocks, metals, and any life would simply cease to be, replaced by a chaotic soup of particles operating under new rules. T equals 1 year. The bubble is 1 light year across. If it formed in our galactic neighborhood, it's consumed hundreds of star systems. Every star encountered by the expanding wall would be snuffed out instantly. Nuclear fusion might not work the same way inside the bubble, or atomic nuclei might not be stable. Countless hypothetical civilizations would be erased without warning, without even the possibility of knowing what destroyed them. T equals 100,000 years. The bubble is 100,000 light years across, encompassing a significant fraction of the Milky Way galaxy. Hundreds of billions of stars have been destroyed or transformed into unrecognizable stellar remnants. The galactic core has been consumed. The spiral arms are being erased as the bubble expands outward at the ultimate speed limit. T equals 2.5 million years. The bubble reaches Andromeda, our nearest large galactic neighbor. The collision between the bubble wall and Andromeda's stars would be spectacular if anyone remained alive to observe it. But there would be no observers. Everything in the bubble's path is gone. T equals tens of billions of years. The bubble encompasses our entire observable universe and continues expanding into regions we can never see, destroying galaxies we'll never know existed. The universe doesn't end, it transforms. The bubble interior might have entirely different physics, different constants, different force strengths, perhaps different numbers of spatial dimensions. Whatever exists there wouldn't recognize or be recognized by beings from our false vacuum. And remember, this all happens at light speed. There is no warning, no time to prepare, no possibility of evacuation or escape. The destruction is simultaneous with the awareness of destruction. The possibility of vacuum decay has been known to physicists since the 1970s, but for decades it remained an esoteric concern, discussed primarily in theoretical papers with limited broader attention. Several times, physicists raised alarms about experiments or scenarios that might trigger vacuum decay, only to be dismissed or ignored. In 1983, physicists Martin Rees and Piet Hat published a paper examining whether particle accelerator experiments could trigger dangerous transitions. They were concerned that collisions at sufficiently high energies might create conditions favoring vacuum decay or other catastrophic phase transitions. Their calculations suggested the risk was negligible, but the very fact they published such analysis indicated the physics community was taking the possibility seriously. When CERN began planning the Large Hadron Collider in the 1990s, some physicists raised concerns about potential catastrophic risks. In addition to worries about creating dangerous black holes, which proved unfounded, there were concerns about vacuum decay. Could colliding protons at an unprecedented energies trigger a transition to true vacuum? CERN commissioned safety studies, published in 2003 and updated in 2008. The reports concluded that LHC operations posed no risk of vacuum destabilization. The reasoning was simple. Cosmic rays strike Earth's atmosphere with energies far exceeding anything the LHC produces. These ultra-high-energy cosmic rays, some with energies up to 10 to the 20th eV, compared to the LHC's 10 to the 13th eV, have been bombarding Earth for billions of years. If such collisions could trigger vacuum decay, it would have happened long ago. The fact that we're still here demonstrates that particle collisions, even at extreme energies, don't nucleate vacuum decay bubbles. This cosmic ray argument is compelling, but not airtight. Cosmic ray collisions produce particles moving at nearly light speed relative to Earth. LHC collisions produce particles in the lab frame, initially at rest before they move apart. Some physicists argued these might be relevantly different scenarios. However, the overwhelming consensus was that cosmic rays provided adequate safety evidence. After the Higgs discovery in 2012, when calculations revealed our vacuum's metastability, concerns resurfaced. If we're in a false vacuum, does any high-energy process risk triggering decay? Again, the cosmic ray argument provided reassurance, but it also highlighted an uncomfortable truth. We're conducting experiments at energy frontiers, probing physics we don't fully understand, in a universe that might be fundamentally unstable. In 2013, physicist Philip Burda and colleagues published calculations suggesting that quantum black holes, if they exist at energies higher than those accessible to us, could catalyze vacuum decay. These hypothetical black holes would create regions of extreme space-time curvature where the probability of Higgs field tunneling dramatically increases. If Planck-scale black holes form and evaporate in the early universe or in other high-energy environments, they could trigger vacuum decay. This wasn't an immediate concern for LHC operations. The energies required are far beyond our reach. But it highlighted that unknown physics at higher energy scales might pose risks we can't assess with current knowledge. We're like children playing with matches near a gas leak we don't know exists. We might be fine, or we might be moments from catastrophe, and our ignorance prevents us from knowing which. Today's scientific consensus on vacuum decay can be summarized as probably real, probably far in the future, but with troubling uncertainties. The probably real part comes from standard model calculations. Using our best measurements of fundamental constants, the vacuum appears metastable. This isn't controversial among physicists familiar with the calculations. The energy landscape has a false vacuum, where we are, and a true vacuum, lower energy, separated by a barrier. Tunneling through that barrier is possible via quantum mechanics. The probably far in the future part comes from calculating the tunneling rate. With current parameters, the vacuum's half-life, the time for a 50% probability of decay occurring somewhere in a volume the size of our observable universe, is estimated at 10 to the 139 years or longer. To put this in perspective, the universe is currently 13.8 billion years old, approximately 10 to the 10 years. The vacuum half-life is 10 to the 129 times longer than the current age of the universe. Numbers this large are effectively meaningless to human intuition. They're so vast that for any practical purpose, the probability of vacuum decay in the lifetime of our sun, our galaxy, or even our observable universe is essentially zero. We're safer from vacuum decay than almost any other imaginable catastrophe. But troubling uncertainties temper this reassurance. Several factors could significantly change the risk assessment. Unknown physics beyond the standard model. Our calculations assume the standard model is complete up to very high energies. But we know it's incomplete. It doesn't include gravity, dark matter, or dark energy. New physics beyond the standard model could stabilize the vacuum, good news, or destabilize it further, bad news. We simply don't know.
Gravitational effects. The calculations typically ignore gravity, but gravity can't be ignored at very high energies or around extreme objects like black holes. General relativity and quantum mechanics don't play well together, and we lack a complete theory of quantum gravity. How gravity affects vacuum stability is unknown. Higher dimensional space. String theory and other frameworks propose additional spatial dimensions beyond the three we experience. If these exist, the vacuum stability calculations change. Higher dimensional effects could stabilize or destabilize the vacuum. Without knowing whether extra dimensions exist or how they're configured, we can't be certain about stability. Inflationary history. If the universe underwent cosmic inflation in its earliest moments, exponential expansion driven by a field in a false vacuum state, that inflation field eventually decayed to the true vacuum, causing inflation to end. Did this decay somehow affect the Higgs field stability? Could remnants of inflation dynamics influence current vacuum stability? These questions lack definitive answers. Anthropic selection. Perhaps we exist in a metastable vacuum precisely because absolutely stable vacua are rare in the multiverse. Anthropic reasoning suggests observers can only exist in universes where the vacuum hasn't decayed. This explains why we observe metastability, but doesn't make it less real or less dangerous. It just reframes the question. These uncertainties mean we can't be completely confident in our calculations. The standard estimate of 10 to the power of 139 years could be off by many orders of magnitude. Maybe the true half-life is 10 to the power of 120 years. Still unimaginably long, but the uncertainty itself is troubling. We're making predictions about reality's fundamental stability based on incomplete knowledge. And there's one more unsettling thought. If vacuum decay is truly random and unpredictable, governed by quantum probability, then it doesn't matter how long the half-life is. It could happen tomorrow. Probability isn't causation. Just because something has 1 in 10 to the 100 odds doesn't mean it won't happen on the first try. It's vastly unlikely, but not impossible. This is where the evidence forces us to confront an uncomfortable possibility, that we exist in a fundamentally precarious reality, one that could cease to exist at any moment through processes we can observe but not prevent, understand but not control.
The question of vacuum stability hinges critically on precise measurements of fundamental constants. Get these measurements wrong by even small amounts, and the stability assessment changes dramatically. This has driven intense efforts to measure the Higgs boson and top quark masses with ever greater precision. When the Higgs was first discovered in 2012, its mass was measured as approximately 125 GeV, with an uncertainty of about 0.5 GeV. By 2024, after analyzing vastly more collision data, CERN physicists have refined this to 125.25 plus or minus 0.17 GeV. This improvement from 0.5 GeV to 0.17 GeV uncertainty might not sound dramatic, but it significantly constrains the stability calculations. Similarly, the top quark mass has been measured with increasing precision. The current world average mass is 172.52 plus or minus 0.32 GeV, combining measurements from both the LHC and the now retired Tevatron collider. Every decimal place matters. Shift the top quark mass by just 1 GeV, and the vacuum stability lifetime changes by orders of magnitude. In 2018, physicist Dario Brutazzo led an analysis incorporating these refined measurements along with improved calculations of quantum corrections. His team's conclusion: the vacuum is metastable with high confidence. We are in a false vacuum, not the true lowest energy state. The lifetime estimates remain enormously long, around 10 to the 140 years, but the metastability itself is now established more firmly than before. However, this precision cuts both ways. While measurements have confirmed metastability, they've also revealed we're extraordinarily close to the boundary between metastability and absolute stability. If the Higgs mass were just 1 to 2 GeV lighter, or if the top quark were slightly heavier, our vacuum would be in the absolutely stable regime, never capable of decay no matter how long we wait. This proximity to the boundary seems almost too coincidental. Physicists have calculated that the parameter space where vacuum is absolutely stable versus metastable versus immediately unstable covers vast ranges. Yet our measured values place us within a few percent of the stability boundary. Why? Some see this as evidence for fine-tuning requiring explanation. Perhaps anthropic selection. Only universes with parameters near the boundary last long enough for life to evolve before vacuum decay occurs. Universes in the absolutely stable regime might exist but lack other features necessary for life. Universes in the unstable regime decay too quickly for structure to form. Others propose that deeper physics we haven't discovered yet explains the near-boundary values. Perhaps there's a symmetry or dynamical principle that naturally drives parameters toward the stability boundary. String theory, supersymmetry, or other beyond-standard model physics might provide mechanisms that explain these otherwise mysterious coincidences. A third possibility is darker. Maybe there's no deep explanation. Maybe we just happen to exist at a time and place where the vacuum hasn't decayed yet, but vast regions of the multiverse have already transitioned, creating expanding bubbles of true vacuum sweeping through cosmic space. We wouldn't know about these bubbles unless one was heading toward us, and we'd only detect it the instant before it destroyed us. The early universe provides another window into vacuum stability. In the first fraction of a second after the Big Bang, temperatures and energy densities were far higher than anything we can create in particle accelerators. If high energies catalyze vacuum decay, the early universe should have been a particularly dangerous period. According to current cosmological models, the universe underwent a period called inflation, approximately 10 to the power of -36 seconds after the Big Bang. During inflation, space expanded exponentially fast, driven by the vacuum energy of a field called the inflaton. This field existed in a false vacuum state during inflation, then transitioned to the true vacuum, ending inflation and reheating the universe with ordinary matter and radiation. Here's what's interesting. Inflation involved a false vacuum transition, exactly the kind of process we're worried about for the Higgs field. The inflaton field tunneled or rolled bound from its false vacuum to true vacuum. The universe survived this transition. In fact, it's the transition that created the conditions for structure formation, galaxies, stars, and eventually life. But inflation's false vacuum and the Higgs false vacuum are different fields. Just because one false vacuum successfully transitioned doesn't guarantee the other won't catastrophically decay. However, the early universe's history does provide evidence that false vacuum states can exist, persist for some time, and transition without destroying everything. In 2014, researchers led by Anders Andreasen at Harvard calculated whether the high temperatures in the early universe might have triggered Higgs vacuum decay. Their models included temperature effects on the Higgs potential. At extremely high temperatures, the effective potential changes shape, potentially stabilizing the false vacuum. Their results suggested that during the very early universe, at temperatures above 10 to the power of 15 GeV, the Higgs vacuum was actually stable, not metastable. The high temperature changes the potential landscape, eliminating the true vacuum minimum or making it inaccessible. Only as the universe cooled did the metastable nature emerge. This is reassuring. It means the most dangerous period, energy-wise, didn't pose a threat. But it also means that once the universe cooled below a certain threshold, it entered the metastable regime, where it has remained for nearly 14 billion years. We've been living on borrowed time since the universe was about 1 second old. Observations of the cosmic microwave background, the afterglow of the Big Bang, provide indirect evidence about vacuum stability in the early universe. Any vacuum transitions occurring after the CMB was emitted, about 380,000 years after the Big Bang, would have left signatures, unusual temperature fluctuations, or distortions in the CMB spectrum. We see no such signatures, confirming that vacuum decay hasn't occurred in the observable universe since then. Looking even further back, the success of Big Bang nucleosynthesis, the formation of light elements in the first few minutes after the Big Bang, tells us that physics was normal, consistent with current laws during that crucial period. If vacuum decay had occurred, particle masses would have changed, altering the nuclear reactions that formed helium, deuterium, and lithium. The observed abundances of these elements match predictions based on stable physics, confirming no vacuum transition occurred. So, the early universe was either in a stable configuration or has been metastable for the entire history we can observe. We've survived 13.8 billion years without vacuum decay. This is encouraging, but doesn't eliminate the risk. It just shows we've been lucky so far. Given the estimated half-life of 10 to the power of 140 years, surviving a mere 10 to the power of 10 years doesn't significantly reduce the probability that decay could still occur. Black holes represent some of the most extreme environments in the universe, regions where gravity becomes so intense that space-time itself breaks down into a singularity. These extreme conditions raise a troubling question: could black holes trigger vacuum decay? The concern is that near a black hole's event horizon, or especially inside it approaching the singularity, the intense gravitational fields might enhance quantum tunneling of the Higgs field. Vacuum decay probability depends on energy density and space-time curvature. Black holes provide both in extreme measure. In 2015, physicist Philip Burda and colleagues at the University of Leiden published calculations examining whether black holes could catalyze vacuum decay. Their work built on earlier studies by Gregory, Moss, and Withers in 1990, who had shown that black holes could indeed enhance false vacuum decay rates under certain conditions. Burda's team found that stellar mass black holes, roughly 3 to 100 solar masses, and supermassive black holes, millions to billions of solar masses, don't pose significant threat. While they do slightly enhance decay probability in their vicinity, the effect is negligibly small. The universe contains billions of black holes, and if they were efficient vacuum decay catalysts, decay would likely have occurred long ago. However, hypothetical primordial black holes, tiny black holes that might have formed in the very early universe, could be more dangerous. If black holes with masses near the Planck scale, about 10 to the power of -5 grams, existed, they would create regions of extreme curvature at microscopic scales. Quantum effects become dominant at these scales, potentially dramatically increasing tunneling probability. The good news is that Planck-scale black holes, if they exist, evaporate almost instantly through Hawking radiation. They don't persist long enough to catalyze extensive vacuum decay. But during their brief existence, they might create small bubbles of true vacuum. Whether these bubbles would collapse back to false vacuum or begin expanding is unclear. The physics at these extreme scales is uncertain. More troubling are the implications for larger primordial black holes. If primordial black holes with masses between 10 to the power of 15 grams, asteroid-sized, and 10 to the power of 20 grams, moon-sized, exist in sufficient numbers, they could collectively present a vacuum decay risk. These black holes would evaporate over timescales from thousands to trillions of years through Hawking radiation, but during their lifetimes, they'd create regions of enhanced vacuum decay probability. Current observations haven't definitively detected primordial black holes, though they remain a candidate for dark matter. If dark matter consists partially of primordial black holes in dangerous mass ranges, they could be dispersed throughout the universe, each slightly increasing the overall probability of vacuum decay. With billions or trillions of such black holes, the cumulative risk might be non-negligible. There's also the question of what happens inside black holes. Beyond the event horizon, approaching the singularity, physics becomes increasingly speculative. We lack a theory of quantum gravity that reliably describes these conditions. Perhaps at the singularity itself, the Higgs field is forced through every possible value, including values that would trigger vacuum decay. If vacuum decay nucleates inside a black hole, would it escape? This is a profound question. Information, matter, and light can't escape from inside a black hole's event horizon. But a bubble of true vacuum expanding at light speed might be different. As the bubble grows, it would consume the black hole itself, potentially releasing whatever was trapped inside. Alternatively, vacuum decay inside a black hole might remain trapped, creating a region of true vacuum causally disconnected from the external universe. Each black hole could be its own little bubble universe with different physics, forever separated from our false vacuum universe by the event horizon. If so, stellar mass black holes would be harmless to us, even if vacuum decay occurs inside them. But we don't know. Our theories break down at the boundaries where general relativity meets quantum mechanics. Black holes exist precisely at those boundaries. They might be perfectly safe, or they might be ticking bombs scattered throughout the cosmos, each one a potential nucleation site for reality-ending vacuum decay.
Perhaps the strongest evidence for vacuum stability, or at least for the safety of high-energy particle collisions, comes from cosmic rays. These are particles, mostly protons, from space that strike Earth's atmosphere at enormous energies, some far exceeding anything achievable in particle accelerators. The highest energy cosmic ray ever detected, observed by the Fly's Eye experiment in 1991, had an energy of approximately 3 × 10⁻20 electron volts. This is about 30 million times more energetic than the highest energy collisions at the LHC. It was dubbed the "Oh my God" particle due to its improbable energy, comparable to a baseball traveling at 100 kilometers per hour, but compressed into a single subatomic particle. Such ultra-high energy cosmic rays are rare but not unique. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah have detected dozens of cosmic rays with energies above 10⁻19 eV. Earth is constantly bombarded by lower energy cosmic rays, with millions hitting every square meter of atmosphere every second. These cosmic ray collisions have been occurring throughout Earth's 4.5 billion year history. They've struck not just Earth, but every planet, moon, asteroid, and comet in the solar system. They've bombarded countless other worlds around countless other stars. If particle collisions at these energies could trigger vacuum decay, the universe would have vast numbers of independent chances for it to occur. The fact that we're still here, that the universe hasn't already been consumed by an expanding bubble of true vacuum, provides strong evidence that high-energy particle collisions don't efficiently nucleate vacuum decay. This is the cosmic ray argument used to reassure concerns about accelerator safety. But there are caveats. First, cosmic ray collisions differ from accelerator collisions in their reference frame. Cosmic rays typically strike stationary atmospheric particles, producing collision products that move at nearly light speed in one direction. Accelerator collisions often involve particles moving toward each other, producing collision products that are initially at rest or moving slowly in the lab frame before separating. Some physicists have argued this difference might matter. Perhaps vacuum decay requires specific conditions, certain particle configurations, certain energy distributions, or particles remaining in close proximity for certain durations that are more likely in accelerator collisions than cosmic ray collisions. This seems unlikely, but without complete theoretical understanding, we can't be absolutely certain. Second, cosmic ray energies, while very high, are still far below the Planck energy scale, 10⁻19 GeV, where quantum gravity effects become dominant. The Oh my God particle had energy around 10⁻11 GeV, impressively high, but still 8 orders of magnitude below Planck scale.
If vacuum decay risk increases dramatically at energies approaching Planck scale, cosmic rays haven't fully tested those regimes. Third, the spatial distribution matters. Cosmic rays strike random locations across vast cosmic volumes. If vacuum decay requires reaching high energies in stable, confined regions, like inside particle accelerators or possibly in the cores of neutron stars, then cosmic rays might not provide complete safety testing for these scenarios. Despite these caveats, the cosmic ray argument remains compelling. Nature has been running ultra-high energy collision experiments for billions of years across trillions of locations. The fact that vacuum decay hasn't occurred suggests either that our vacuum is more stable than metastability calculations suggest, or that high-energy collisions aren't efficient triggers for decay, or both. Still, there's an unsettling thought. Perhaps vacuum decay has occurred, and the bubbles are simply expanding toward us but haven't arrived yet. A bubble that nucleated in a distant galaxy a billion years ago would now be a billion light-years in radius, consuming thousands of galaxies as it expands. We wouldn't know about it until the moment it reached us. Traveling at light speed, it would arrive simultaneously with any light or gravitational wave signal announcing its existence. The observable universe could be filled with expanding bubbles of true vacuum, all racing toward us at the ultimate speed limit. We would see nothing until the instant of impact. This represents just one piece of a much larger puzzle emerging from precision measurements, theoretical calculations, and observational constraints. The evidence points consistently toward a troubling conclusion. We exist in a fundamentally metastable reality where catastrophic transformation is possible but unpredictable. The fact that our vacuum sits precariously near the stability boundary raises profound questions about why the universe has the properties it does. This connects to the anthropic principle, the observation that the universe must have properties compatible with the eventual emergence of observers like us. The strong anthropic principle argues that the universe must have life-permitting properties because otherwise we wouldn't be here to observe it. This seems tautological but carries real explanatory weight when combined with multiverse theories. If countless universes exist with different physical constants, we necessarily find ourselves in one where the constants permit our existence. Applied to vacuum stability, perhaps in the multiverse, some universes have stable vacua, some have metastable vacua, and some have unstable vacua that decay almost immediately after the Big Bang. We can't exist in universes with unstable vacua. They transition before stars and galaxies can form. We might not exist in certain stable vacua either, if the stable configuration has physics that doesn't permit complex chemistry or long-lived stars. The metastable regime might be a Goldilocks zone, stable enough to last billions of years for life to evolve, but not so locked in stability that the physics is incompatible with life's requirements. This would explain why we observe metastability. It's a rare configuration in the multiverse, but it's exactly the configuration that permits observers to arise. However, this anthropic explanation has troubling implications. If we're in a metastable vacuum solely because stable vacua don't support life, then we should expect to be near the minimum lifetime compatible with our existence. In other words, the vacuum should decay relatively soon on cosmic timescales, perhaps in the next few billion years rather than 10 to the power of 140 years. Physicist Don Page has argued that under certain anthropic assumptions, we should be surprised the vacuum has lasted as long as it has. If countless observer-containing universes exist with different vacuum lifetimes, we're most likely to find ourselves in one near the median of the distribution. The fact that our vacuum has lasted nearly 14 billion years and appears capable of lasting vastly longer might be evidence against simple anthropic explanations. Another fine-tuning puzzle involves the Higgs mass itself. Why is it 125 GeV and not some other value? Quantum corrections to the Higgs mass should push it toward extremely high values, near the Planck mass, unless there's a remarkable cancellation of quantum effects. This is the hierarchy problem in particle physics, one of the deepest unsolved mysteries. Supersymmetry, a proposed extension of the Standard Model, would naturally explain the Higgs mass by introducing partner particles that cancel the quantum corrections. But the LHC has found no evidence of supersymmetry up to the energies explored so far. This has led some physicists to propose that the Higgs mass is anthropically selected in a multiverse. It has the value it does because other values would be incompatible with life. But if the Higgs mass is anthropically fine-tuned, then by the same reasoning, the metastability of the vacuum might also be anthropically selected. We exist in a universe with a Higgs mass that happens to place us at the stability boundary, because this is the only configuration compatible with our existence. This doesn't eliminate the danger. We're still in a metastable state that could decay. It just provides a framework for understanding why we find ourselves in such an improbable configuration.
The vacuum stability issue connects to another profound puzzle in physics, the cosmological constant problem. The cosmological constant describes the energy density of empty space itself, the vacuum energy that drives the universe's accelerating expansion. This is often called dark energy. Measurements show the cosmological constant has a tiny but non-zero value, approximately 10 to the power of negative 47 GeV to the power of 4 in natural units. This is one of the smallest numbers in all of physics. But here's the problem. Quantum field theory predicts that vacuum energy should be enormous, roughly 10 to the power of 113 GeV to the power of 4, when including contributions from all quantum fields. This is a discrepancy of 120 orders of magnitude, the worst prediction in the history of physics. Something is canceling out the quantum contributions to vacuum energy, reducing it from 10 to the power of 113 to 10 to the power of negative 47, but we don't know what or why. This is the cosmological constant problem, and it remains unsolved after decades of effort. The connection to vacuum decay is subtle but important. Both involve the energy of the vacuum state. The cosmological constant measures the actual energy density of our current vacuum. Vacuum decay involves transitioning to a state with lower energy density. But if the true vacuum has even lower energy than our current false vacuum, what determines these energy levels, and how do they relate to the quantum field theory predictions? One possibility is that the enormous quantum contributions to vacuum energy don't actually exist, that there's some principle or mechanism that cancels them exactly, reducing the vacuum energy to the tiny observed value. If this mechanism exists, it might also affect vacuum stability, perhaps making our vacuum more stable than Standard Model calculations suggest. Another possibility involves extra dimensions or string theory. In these frameworks, vacuum energy depends on how extra dimensions are configured, their shape, size, and topology. Perhaps the false vacuum and true vacuum represent different configurations of extra dimensions, and the energy difference is related to geometric properties we don't yet understand. A third, more troubling possibility
Maybe there's no deep explanation. Maybe in a vast multiverse of universes with different vacuum energies, we happen to exist in one with the observed value simply because other values are incompatible with life. Universes with large positive cosmological constants expand so rapidly that galaxies never form. Universes with large negative cosmological constants collapse back on themselves too quickly for stars to ignite. This anthropic explanation for the cosmological constant, proposed by physicist Steven Weinberg in 1987, has gained considerable traction despite being philosophically unsatisfactory. If it's correct, it suggests that vacuum energy, Higgs mass, and perhaps many other physical constants are environmentally determined rather than following from deep principles. We're in a universe with these values because these are the values compatible with observers. But this raises a disturbing scenario. If the cosmological constant is anthropically selected from a landscape of possibilities, and if vacuum decay transitions us to a different region of this landscape with a different cosmological constant, the decay might be deadly not just because it changes particle masses, but because it changes the expansion rate of space. A vacuum transition could create a bubble where the cosmological constant is much larger or smaller, making that bubble region immediately uninhabitable. Vacuum decay also connects to the deepest mysteries in quantum mechanics itself. The metastable nature of the vacuum means it exists in a quantum superposition of states, simultaneously in the false vacuum and having some probability amplitude for being in or transitioning to the true vacuum. In standard quantum mechanics, systems exist in superposition until measured. Measurement causes wave function collapse. The system transitions from superposition to a definite state. But what counts as measurement? This is the infamous measurement problem, one of quantum mechanics' most profound conceptual puzzles. Does the vacuum need to be measured to collapse from its quantum superposition? If so, measured by what? Or does the vacuum spontaneously collapse without measurement through some objective collapse mechanism that operates independently of observers? Some interpretations of quantum mechanics avoid these questions by denying that wave function collapse is real. The many worlds interpretation says the universe constantly branches into parallel versions, each experiencing different outcomes of quantum events. In this view, vacuum decay doesn't have a single probability of occurring. Rather, the universe continuously branches, with vacuum decay occurring in some branches and not in others. If many worlds is correct, then somewhere in the vast multiverse of quantum branches, vacuum decay has already occurred. In fact, it's occurring right now in countless branches, creating bubbles that consume those branch universes. We simply happen to exist in branches where decay hasn't occurred yet. But from a God's eye view, every quantum possibility is realized somewhere. This doesn't provide comfort. We still face the possibility of vacuum decay in our branch, but it does reframe the question. Instead of asking, when will vacuum decay occur, we should ask, how rare are the branches where vacuum decay hasn't yet occurred? If our branch type becomes exponentially rarer over time as more branches experience decay, then from a statistical perspective, we should expect decay sooner rather than later. The pilot wave interpretation of quantum mechanics offers a different perspective. In this view, particles have definite positions at all times, guided by a quantum wave that determines their motion. There's no wave function collapse, just continuous evolution following deterministic laws. Vacuum decay would be a deterministic process. It will happen when the particle trajectories reach configurations that trigger the transition. But pilot wave theory has its own peculiarities. The wave guiding particle motion is non-local, instantaneously connecting all particles across the universe. How does this non-locality interact with vacuum decay? If the Higgs field throughout the universe is connected by non-local quantum correlations, does this affect where and when decay bubbles might nucleate? The spontaneous collapse theories, like the GRW or Ghirardi-Rimini-Weber theory, propose that wave functions randomly collapse at a rate depending on the size and complexity of the system. Large objects collapse frequently, microscopic quantum systems rarely. Where does the cosmic Higgs field fall on this spectrum? If it's constantly undergoing spontaneous collapse, this might either stabilize it, preventing coherent tunneling, or destabilize it, causing random fluctuations that could trigger decay. These questions aren't merely philosophical. The interpretation of quantum mechanics might affect the actual probability and timing of vacuum decay. If consciousness causes collapse, as some interpretations suggest, then the emergence of conscious observers throughout the universe might influence vacuum stability. If objective collapse mechanisms exist, they could affect tunneling rates. If many worlds is correct, the question shifts from will it happen to in what fraction of branches does it happen? Vacuum decay also connects to the black hole information paradox, one of the deepest problems in theoretical physics. When matter falls into a black hole, does the information it carries disappear when the black hole evaporates through Hawking radiation? This seems to violate quantum mechanics, which requires information conservation. Stephen Hawking's original calculations suggested information is lost, but this creates a paradox. If information can be destroyed, quantum mechanics is wrong. Leonard Susskind, Gerard Tufte, and others argued that information must be preserved, perhaps encoded on the black hole's event horizon through holographic principles. Vacuum decay presents a similar paradox. When a bubble of true vacuum expands through a region of space, it erases all structures in that region: atoms, molecules, people, planets, stars. The information describing those structures appears to be lost, transformed into the homogeneous true vacuum state inside the bubble. But if quantum mechanics requires information conservation, where does the information go? Is it encoded in the bubble wall somehow, like information on a black hole horizon? Does the true vacuum state inside the bubble contain all the information about what existed in the false vacuum, just in a form we can't access or decode? Or does vacuum decay genuinely destroy information, revealing limitations in quantum mechanics itself? Some theorists propose that the bubble wall acts like a cosmic screen where information is holographically encoded. As the wall expands through space, it records everything it encounters, preserving information in two-dimensional form on the expanding surface. This would make vacuum decay more like a black hole horizon than a simple annihilation. Information is preserved but inaccessible to observers inside the bubble. Others suggest that the true vacuum isn't truly featureless. Perhaps it contains excitations or patterns that encode the information from the false vacuum structures it destroyed. The particles inside a true vacuum bubble might have different masses and interaction strengths, but the specific values and quantum states might contain encoded information about what the vacuum consumed. A more radical possibility: maybe information conservation breaks down at the boundaries where quantum mechanics meets gravity and extreme energy scales. Vacuum decay might represent a situation where our fundamental principles, quantum mechanics, relativity, thermodynamics, all break down simultaneously, revealing that reality at the deepest level operates according to principles we haven't yet discovered. What scientists found in studying vacuum decay has led inexorably to a disturbing conclusion. Multiple lines of evidence from particle physics, cosmology, quantum mechanics, and gravitational theory all point towards the same unsettling truth. We exist in a universe whose fundamental state is metastable, capable of catastrophic transition at any moment through processes we can calculate but not prevent, understand but not control. The truly terrifying implications are only beginning to reveal themselves. To fully understand vacuum decay, we must explore the landscape of possible vacuum states, the vast space of configurations that quantum fields can occupy. This landscape concept comes from string theory, but applies more broadly to quantum field theory in general. Imagine a multi-dimensional surface where each point represents a different configuration of quantum fields. The height at each point represents the energy density of that configuration. Valleys are low energy states. Peaks are high energy states. Our universe currently sits in one valley, the false vacuum. But there are other valleys, potentially countless others, each representing a possible true vacuum with different physics. The shape of this landscape is extraordinarily complex. In simple models with a single quantum field like the Higgs, the landscape might have just one false vacuum and one true vacuum, separated by an energy barrier. But in realistic models with multiple quantum fields, the Higgs, top quarks, all the other standard model fields, and potentially unknown fields beyond the standard model, the landscape becomes vastly more complicated. String theory suggests the landscape might have 10 to the 500 or more distinct vacuum configurations, each corresponding to different ways of compactifying the extra spatial dimensions that string theory requires. Each configuration would have different particle masses, different force strengths, possibly even different numbers of macroscopic spatial dimensions. The landscape would be a vast cosmic menu of possible physical laws. In this picture, our false vacuum is just one valley among countless others. Vacuum decay would be a transition from our valley to a neighboring valley with lower energy. But which neighboring valley? There might be multiple possible true vacua, each lower in energy than our current state, but with different properties. The vacuum might decay to one, or possibly cascade through several successive decays until reaching the absolute lowest energy configuration. Each transition would change the laws of physics. The first transition might change particle masses slightly, making atoms unstable but leaving some structures intact. The next transition might change force strengths, completely restructuring how matter behaves. A third transition might alter the number of spatial dimensions, creating a reality utterly incomprehensible to beings evolved in our 3+1 dimensional spacetime. This multi-stage decay possibility means that even after one vacuum transition, the danger doesn't end. The new vacuum might itself be metastable, capable of further decay. The universe could undergo a cascade of transitions, each one erasing the structures created in the previous phase and establishing new physical laws more alien than the last. The landscape also includes vacua with positive cosmological constant, accelerating universes like ours, and vacua with negative cosmological constant, contracting universes. A vacuum transition could change not just particle physics, but the overall expansion or contraction of space itself. A bubble with negative cosmological constant would immediately begin collapsing, crushing everything inside before the new physics even mattered. Researchers studying the landscape have identified certain patterns. Low-energy vacua tend to have weaker forces and lighter particles. High-energy vacua have stronger forces and heavier particles. Our vacuum sits somewhere in the middle, not the highest energy possible, but far from the lowest. This suggests that if decay occurs, we're likely transitioning to a state with weaker forces and lighter particles. But lighter particles mean weaker atomic bonds and less stable nuclei. The atoms that compose stars, planets, and living beings might not be stable in the true vacuum. Even if macroscopic structures somehow survived the bubble wall passage, unlikely. They'd quickly dissolve as their constituent atoms decayed or transmuted into unfamiliar particle configurations. The landscape concept also helps explain the fine-tuning puzzles we discussed earlier. With 10 to the power of 500 possible vacuum configurations in the landscape, a tiny fraction might have properties compatible with complex structure formation and life. Anthropic selection would automatically place us in one of these rare compatible configurations, explaining why our physical constants seem so precisely tuned. But this raises a chilling possibility. If we're anthropically selected to be in a life-compatible vacuum, and if most vacua aren't life-compatible, then we're probably not in the lowest energy vacuum, which would be lifeless. We're in a metastable vacuum that's life-compatible but higher energy than the true ground state. The decay we're avoiding is inevitable because the ground state is inhospitable. Nature wants to transition to lifelessness, and we're living in a temporary exception. The physics community holds diverse views on vacuum decay, reflecting genuine uncertainty about both the likelihood and the implications of this scenario. The pragmatic majority. Most particle physicists accept that the vacuum is metastable based on standard model calculations, but they emphasize the astronomical timescales involved. Brian Greene, Stephen Hawking, before his death, and Lisa Randall have all acknowledged vacuum metastability while noting that the decay timescales of 10 to the 140 years or longer make it essentially irrelevant for any practical purpose. These physicists argue we shouldn't worry about vacuum decay because the timescale is so long that countless other cosmological processes, star death, black hole evaporation, possible big rip or big crunch, will occur first. Unknown physics beyond the standard model might stabilize the vacuum, and anthropic reasoning suggests we wouldn't exist if decay were likely in the near future. Other existential risks, like climate change, nuclear war, or AI risk, are far more immediate concerns. The concerned minority. A smaller group takes vacuum decay more seriously as a genuine existential risk. Physicist Katie Mack, author of The End of Everything, emphasizes that, while unlikely, vacuum decay is possible and would be absolutely catastrophic. She argues we shouldn't dismiss low-probability extinction events just because they're improbable. When the stakes are infinite, even tiny probabilities matter. Philosopher Nick Bostrom has included vacuum decay in analyses of existential risk, though he ranks it below more immediate threats like AI or nuclear war. His concern is that our probability estimates might be wrong by orders of magnitude due to unknown physics, and that, even with correct estimates, quantum randomness means extremely unlikely events can occur at any time. The optimists. Some physicists believe vacuum decay is less likely than standard calculations suggest. Frank Wilczek, Nobel laureate in physics, has argued that new physics beyond the standard model, perhaps supersymmetry or additional Higgs-like fields, might stabilize our vacuum. He notes that we're right at the edge of the metastability boundary, which could indicate we're actually in a stable regime once corrections from unknown physics are included. Lawrence Krauss has suggested that gravitational effects, not fully included in current calculations, might significantly alter the vacuum stability assessment. Gravity couples to energy density, and the energy released during vacuum transitions could create gravitational feedback that stabilizes against decay or changes the bubble expansion dynamics. The string theorists. Physicists working in string theory and the multiverse hypothesis tend to view vacuum decay through a different lens. Leonard Susskind, André Linde, and Max Tegmark emphasize that if the landscape contains 10 to the 500 vacua, then vacuum decay is constantly occurring throughout the eternal multiverse. Bubbles nucleate, expand, collide, and create incredibly complex cosmic structures. In this view, we're living inside one bubble in an infinite foam of bubbles, each with different physics. Vacuum decay isn't a threat to existence itself, just to our particular bubble. Other bubbles and other observers will continue to exist. This provides cold comfort. We still get destroyed, but cosmic perspective, existence continues elsewhere. The skeptics. A few physicists question whether the landscape and vacuum decay are even meaningful concepts. Roger Penrose has expressed skepticism about string theory's landscape, arguing that the vast number of vacua might indicate the theory is untestable and unscientific. If we can't predict which vacuum we're in from first principles, are we doing physics or just parameter fitting? Sabine Hassenfelder has criticized fine-tuning arguments and anthropic reasoning, suggesting that vacuum metastability might reflect limitations in our current theories rather than physical reality. She argues we should focus on finding deeper principles that explain our universe's properties without invoking multiverse anthropics or arbitrary landscape configurations. Vacuum decay forces confrontation with profound philosophical questions about existence, knowledge, and meaning. These questions transcend physics and touch on the deepest aspects of human understanding. The problem of induction. Philosopher David Hume argued that we can't rationally justify inductive reasoning, inferring future events from past patterns. Just because the sun has risen every day doesn't logically guarantee it will rise tomorrow. Vacuum decay exemplifies this problem perfectly. The vacuum has been stable for 13.8 billion years. Every observation in physics history has shown consistent laws operating under stable vacuum conditions. Yet this provides no logical guarantee that stability will continue. The next moment could bring vacuum collapse, and all our past evidence would prove irrelevant. This isn't just philosophical nitpicking, it reveals a fundamental limit to scientific prediction. We can calculate probabilities based on theories, but we can't eliminate the possibility of sudden, unpredictable transitions. Reality might not be as orderly as science assumes. Existential vulnerability. Vacuum decay reveals that existence itself is vulnerable in ways we typically don't consider. We worry about death, the end of individual consciousness. We worry about extinction, the end of humanity. But vacuum decay threatens something more fundamental, the end of the possibility of existence itself, at least in forms we'd recognize. This creates a unique form of existential anxiety, not fear of personal death or even species death,
but fear of the universe becoming an alien place where the physics necessary for any life or consciousness no longer operates. It's the fear that reality itself could betray us, that the stage we stand on could suddenly vanish.
The meaning crisis. If the universe could end at any moment through vacuum decay, how do we find meaning? Traditional sources of meaning, legacy, progress, building for the future, all assume some continuity. If the vacuum decays, every human accomplishment disappears instantly and completely. Does this make our actions meaningless? Some philosophers argue no. Meaning isn't determined by duration or ultimate outcomes, but by the quality of experience and the significance of actions in their context. A beautiful life is meaningful regardless of whether it lasts forever. Acts of love, creation, and understanding have intrinsic value that doesn't depend on permanence. Others find this cold comfort. If everything, every thought, every achievement, every moment of joy or suffering can be erased without trace, it's hard to maintain that anything truly matters. Vacuum decay represents the ultimate nihilistic scenario. Even the laws of physics that give structure to existence are temporary and arbitrary. The limits of knowledge. Vacuum decay also reveals epistemological limits. We can calculate probabilities, but we can't predict when or if decay will occur. We can understand the mechanism, but we can't prevent it. We're in the strange position of knowing about a threat we're powerless to address. This differs from other existential risks where knowledge enables action. Knowing about asteroid impacts lets us develop deflection technologies. Understanding nuclear weapons lets us negotiate arms reductions. Comprehending climate change enables mitigation. But vacuum decay offers no such hope. Knowing about it doesn't help us survive it. This creates ethical dilemmas. Should we tell people about vacuum decay? Does spreading awareness of an unpredictable, unpreventable existential threat serve any purpose other than creating anxiety? Or does awareness have intrinsic value, even when it doesn't enable action? These questions lack clear answers. The question of cosmic purpose. If the universe tends toward vacuum decay, if all structure, all order, all complexity eventually gives way to transformed physics in a lower energy state, what does this say about cosmic purpose? Is the universe fundamentally meaningless, with temporary islands of structure in an ocean of transformation? Or might even vacuum decay serve some cosmic purpose we can't yet discern? Some physicists and philosophers speculate that vacuum transitions might be how the universe explores its possibilities, how different physical laws get instantiated, how cosmic evolution occurs. In this view, our vacuum state is just one experiment among countless others, and its eventual decay would be transformation rather than ending, birth of new physics rather than death of old physics. If a vacuum decay bubble is expanding toward us through space, could we detect it before it arrives? This question has occupied theoretical physicists since the possibility of vacuum decay was first recognized. The answer is both technically fascinating and existentially disturbing. The fundamental problem is that the bubble expands at light speed. Any signal warning us of its approach, light, gravitational waves, neutrinos, also travels at light speed. The warning signal and the bubble wall arrive simultaneously. We have zero advance notice. The first indication of doom is doom itself. However, some physicists have proposed subtle ways we might detect evidence of distant vacuum decay, even if we can't detect bubbles heading directly toward us. The key is looking for bubbles that aren't approaching us but are visible elsewhere in the universe, whose light has had time to reach us before their walls do. Observing distant bubbles. If vacuum decay has occurred in the distant universe, we might observe the resulting bubbles as unusual structures. The boundary between false and true vacuum releases enormous energy as the Higgs field transitions. This energy would appear as intense radiation, possibly visible as extremely bright, expanding shells of light. In 2015, astronomers Oscar Hernandez and colleagues proposed that certain types of transient astronomical events might be signatures of vacuum decay. They suggested looking for perfectly spherical shells of radiation expanding at precisely light speed, spectra inconsistent with any known astrophysical processes, acceleration rather than deceleration. Most cosmic explosions slow down, vacuum decay bubbles don't. And no remaining central object. Supernovae leave neutron stars or black holes. Vacuum decay leaves nothing. So far, no confirmed vacuum decay bubble has been observed, but the universe is vast and our observations are limited. We've only surveyed a tiny fraction of cosmic history and cosmic volume. Distant bubbles might exist but be too far for their light to have reached us yet, or they might be obscured by foreground objects, or we might be misinterpreting their signals as natural phenomena. Gravitational wave signatures. The bubble wall creates a discontinuity in space-time, a sharp boundary between different vacuum states with different energy densities. This discontinuity would generate gravitational waves as the bubble expands. In 2019, physicists Toby Offerkuch and colleagues calculated the gravitational wave signature of an expanding vacuum decay bubble. They found that the signal would have distinctive properties, continuous rather than transient emission, increasing in frequency as the bubble approaches, and coming from an extended source rather than a point. Future gravitational wave observatories like LISA, Laser Interferometer Space Antenna, scheduled for the 2030s, or proposed next-generation detectors might be sensitive enough to detect these signatures. If we observed gravitational waves with the right properties coming from a specific direction, it could indicate a vacuum decay bubble expanding in that region. But even this provides limited warning. Gravitational waves travel at light speed. A bubble detected via gravitational waves would still give us zero warning of its arrival. We'd observe the waves at the same instant the bubble wall hits us. The only benefit is that we might observe bubbles in other directions, confirming that vacuum decay occurs and possibly heading toward us from directions we can't yet observe. Cosmic microwave background distortions. If vacuum decay occurred in the early universe before the cosmic microwave background was emitted, about 380,000 years after the Big Bang, it should have left signatures in the CMB. The bubble collision with our region of space would create temperature and polarization anomalies with specific patterns. Physicists have searched for these patterns and found nothing definitive. This tells us that vacuum decay hasn't occurred in our observable universe since before CMD emission, but it doesn't protect us from bubbles nucleating more recently or existing beyond our observable horizon but expanding toward us. The cruel arithmetic of detection. Even if we could somehow detect approaching bubbles, what would we do? There's no escape. The bubble expands at light speed in all directions. We can't outrun it. We'd need faster-than-light travel, which physics forbids. We can't destroy it. It's a fundamental transition in quantum field configuration, not something that can be bombed or deflected.
We might have time to send a final message to other regions of space not yet consumed, warning them that vacuum decay is real and coming. But they'd receive our message at the same time the bubble reached them. The warning and the death blow arrive together. This means detection serves no practical survival purpose. It only provides knowledge, the bitter awareness of what's destroying us in the final moments before annihilation. Whether this knowledge is valuable or merely torturous is a question each person must answer for themselves.
The short answer is almost certainly not. But let's explore the possibilities that physicists and futurists have considered, no matter how speculative or unlikely. Manipulating vacuum energy. In principle, if we could manipulate quantum fields at fundamental levels, we might be able to stabilize the false vacuum. The idea would be to inject energy into the vacuum in ways that raise the energy barrier between false and true vacuum, making tunneling less likely. This would require technology far beyond anything currently conceivable. We'd need to manipulate Higgs field values across vast regions of space using energies comparable to what existed in the early universe. It's unclear if this is even theoretically possible, let alone practically achievable. Moreover, such manipulation might be counterproductive. Adding energy to the vacuum might actually trigger decay rather than prevent it, like heating a supercooled liquid can trigger crystallization. Our interventions could be the catalyst that nucleates the very bubble we're trying to avoid. Escaping to other dimensions. If extra-spatial dimensions exist, as string theory suggests, perhaps we could somehow move into those dimensions to escape vacuum decay in our familiar 3 dimensions. The bubble would expand through our ordinary space, but might not immediately affect the extra dimensions. This is wild speculation based on hypothetical physics. We have no evidence extra dimensions exist, no idea how to access them if they do, and no reason to think they'd provide refuge from vacuum decay. The transition affects fundamental fields that permeate all dimensions, not just the 3 we perceive. Creating safe zones. Could we create localized regions where the false vacuum is artificially stabilized, perhaps using intense magnetic or gravitational fields to alter the effective potential, raising the energy barrier locally? This might be possible in principle, but it faces enormous obstacles. First, the energies required would be astronomical, comparable to the entire output of stars or even galaxies. Second, even if we created a stable region, maintaining it indefinitely while a bubble wall approaches would be impossible. Third, the bubble doesn't just passively wash over regions, it actively destroys structures, including any machinery we'd build to stabilize the vacuum. Uploading and information transfer. A more speculative possibility. If consciousness can be uploaded to computational substrates, and if we had warning of approaching vacuum decay, we might attempt to transmit our uploaded minds at light speed away from the bubble. The idea is that the bubble approaches at light speed from one direction. We'd send information, our uploaded consciousness, at light speed in the opposite direction. The information would always stay ahead of the bubble, at least until the bubble wraps around from the other side of the universe. This buys time, potentially billions of years if we're lucky with the bubble's location, but ultimately it's futile. The bubble expands in all directions. Eventually, it encompasses everything. There's nowhere to run, even at light speed. Surviving the transition. Could we possibly survive inside a vacuum decay bubble? Could structures exist in the true vacuum, operating under its different physics? This seems nearly impossible, but let's consider it. If the true vacuum has significantly different particle masses and force strengths, atoms as we know them can't exist. Our bodies, brains, and any physical structures we've built would dissolve. But perhaps vastly different structures could exist in true vacuum physics. Exotic atoms, strange molecules, unfamiliar forms of organization. If so, could information somehow be preserved across the transition? Could the pattern that constitutes a human mind be translated into true vacuum structures? This seems like fantasy, but the universe is strange. Perhaps consciousness is substrate independent enough to survive even vacuum decay, reconstituting itself in alien physics. Most physicists consider this absurdly optimistic. The transition is violent, releases enormous energy, and fundamentally changes the rules. It's like asking whether a sandcastle survives being hit by a tsunami while simultaneously all the sand turns to water. The answer is no. Structure does not survive such fundamental transformation. Given that vacuum decay is possible, but unpredictable, unpreventable, and unsurvivable, how should humanity respond to this knowledge? What should we do with the awareness that our existence might be temporary in a profound sense? The case for ignoring it. Some argue we should simply not worry about vacuum decay. The probability is so low that it's effectively zero on any timescale relevant to human civilization. We have more immediate existential risks: climate change, nuclear war, AI, that demand attention. Worrying about vacuum decay is like worrying about being struck by a meteor while crossing a busy street. Yes, it's possible, but other dangers are far more pressing. Moreover, since we can't prevent vacuum decay, worrying about it accomplishes nothing except creating anxiety. Why burden ourselves with dread about an unpredictable, uncontrollable threat? Better to focus on threats we can address and leave vacuum decay to physicists studying fundamental reality. The case for productive concern. Others argue that vacuum decay, while unlikely, deserves some attention precisely because it's so catastrophic. We allocate resources to existential risks based on expected value, probability times consequence. Even tiny probability multiplied by infinite consequence yields significant expected value. This doesn't mean devoting massive resources to vacuum decay research, but it suggests we should continue precision measurements of fundamental constants to refine stability calculations, pursue theoretical physics that might reveal stabilizing mechanisms, include vacuum decay in comprehensive existential risk assessments, use it as a reminder that reality is more fragile than everyday intuition suggests. The philosophical response. Perhaps the most meaningful response is philosophical rather than practical. Vacuum decay teaches us about impermanence, uncertainty, and the limits of control. These are ancient themes in philosophy and religion, but modern physics gives them concrete form. Buddhism teaches that all things are impermanent and that suffering comes from clinging to permanence. Vacuum decay is the ultimate impermanence. Even physical law itself is temporary. This doesn't diminish life's meaning, but clarifies it. Meaning comes from the quality of experience, not from duration or permanence. Stoic philosophy emphasizes distinguishing what we control from what we don't. We don't control vacuum decay, so wisdom means accepting it without fear. We control our actions, thoughts, and responses, so wisdom means focusing there. Vacuum decay is a cosmic scale example of the Stoic principle. Some things are up to us, others aren't. Existentialism holds that we create meaning through authentic choices in the face of absurdity. Vacuum decay epitomizes absurdity. The universe could end at any moment for no reason, erasing everything. Existentialist response: live authentically anyway. Choose meaning despite meaninglessness. Act as if our actions matter, knowing they ultimately might not. The scientific imperative. Finally, vacuum decay represents a challenge to science itself. We've discovered a phenomenon we can understand but not control, calculate but not prevent. This humbles us, showing limits to human power even as it demonstrates the power of human understanding. The appropriate response is continued research, not because we'll prevent vacuum decay, but because understanding reality deeply has intrinsic value. Every refinement in our measurements, every advance in theoretical framework, every insight into fundamental physics matters not for practical benefit, but because knowledge is itself worthwhile. Vacuum decay reminds us that we're part of something larger than ourselves. A cosmos that existed before us will likely exist after us and follows rules that transcend human needs or desires. Science is how we connect with that larger reality, how we transcend our limited perspectives and glimpse truth that exists independent of us. Recent breakthroughs in particle physics, cosmology, and quantum field theory have brought us to a strange place. We understand enough to know our existence is metastable, precarious, possibly temporary in ways that were unimaginable to previous generations. But we don't understand enough to know when or if catastrophe will strike, or whether anything lies beyond the transformation. We're suspended between ignorance and knowledge, between safety and danger, between past that gave us structure and a future that might erase it all. If vacuum decay occurs and a bubble of true vacuum forms, what actually exists inside? This question takes us to the boundaries of physics and perhaps beyond, into realms where our current theories break down and speculation necessarily replaces certainty. The immediate aftermath of bubble nucleation would be chaotic, as the Higgs field transitions from false to true vacuum value. It releases potential energy, the difference in energy density between the two states. This energy doesn't disappear, it converts into particles and radiation. The bubble wall would be a region of intense particle creation, temperatures potentially rivaling the early universe. But that's just the transition zone. What about deeper inside the bubble, after the field has fully settled into its true vacuum configuration? Here, physics operates under new rules. The Higgs field's value determines particle masses, so if the true vacuum has a different Higgs value, every fundamental particle has a different mass. Let's imagine a scenario. Suppose the true vacuum has a Higgs field value of 0 instead of our false vacuum's value. This is called the Higgs desert scenario. With 0 Higgs field, fundamental particles would have 0 mass from the Higgs mechanism. Electrons, quarks, the W and Z bosons, all massless. Massless particles travel at light speed, unable to slow down or be confined. Atoms couldn't exist. You can't build atomic structure from particles that zip away at light speed. No atoms means no chemistry, no molecules, no complex structures. The bubble interior would be a soup of massless particles and photons, forever unable to organize into anything we'd recognize. But that's just one possible true vacuum configuration. The true vacuum might have a non-zero Higgs field value, just different from ours. Perhaps electrons become 10 times heavier, quarks become lighter, the relationship between particle masses changes. Would atoms still be possible? Atomic structure depends sensitively on mass ratios. Electrons must be much lighter than protons for atoms to have the right size and binding energy. If that ratio changes significantly, you get weird atoms, maybe with electrons so heavy they're inside the nucleus, maybe with binding energies so weak that atoms dissociate at room temperature equivalent energies. Even if exotic atoms could exist, would they form complex molecules? Chemistry depends on electromagnetic interactions between atoms, and those interactions depend on all the fine details of atomic structure. Change the mass ratios, and chemistry changes. Perhaps no organic molecules could form. Perhaps carbon doesn't bond in ways that permit complex structures. Perhaps water doesn't exist or has completely different properties. There's also the question of nuclear physics. Quarks bind together via the strong force to form protons and neutrons. These nucleons then bind via residual strong force to form atomic nuclei. All this depends on quark masses, gluon properties, and the strength of the strong force. Change the parameters, and nuclear physics changes. Maybe in the true vacuum, protons decay rapidly. Maybe no stable nuclei heavier than helium can form. Maybe nuclear fusion becomes impossible or proceeds uncontrollably. Without stable nuclei, there are no atoms, no chemistry, no possibility of complex structure. Or perhaps, and this is highly speculative, entirely new forms of structure become possible in true vacuum. Maybe there are exotic bound states, novel composite particles, or organizational principles we can't even conceive of because they require true vacuum physics to operate. Perhaps the true vacuum is richer and more complex than our false vacuum, just in ways we can't imagine from our current perspective. Some physicists speculate that consciousness itself might be substrate independent enough to exist in radically different physics. If consciousness is fundamentally about information processing, and if true vacuum physics permits information processing of any kind, maybe consciousness could arise there too. Not human consciousness, but something alien, unrecognizable, yet genuinely aware. This seems extraordinarily unlikely. Consciousness, as we understand it, requires brains, which require chemistry, which requires atoms, which requires specific physics. Change the physics fundamentally, and you don't get different consciousness, you get no consciousness. But our understanding is limited. Perhaps consciousness is more universal than we think, capable of instantiating itself in any physics rich enough to support complex information processing. The truth is, we don't know. We can't know until we have a complete theory of everything that lets us calculate physics in any possible vacuum configuration, and we may never have that theory. The universe inside a vacuum decay bubble might be forever unknowable to beings evolved in the false vacuum. Here's a disturbing thought. What if vacuum decay has already occurred in the distant universe and bubbles are expanding toward us right now? We wouldn't know. The bubbles travel at light speed, which means they're invisible until impact. Light carrying information about the bubble arrives at the same instant the bubble wall does. This raises a chilling possibility. Our observable universe might be surrounded by bubbles expanding toward us from all directions, and we'd have no way to detect them until it's too late. Imagine shells of destruction converging on Earth, each one light years across, moving inexorably at the ultimate speed limit. They could be seconds away or billions of years away, and we couldn't distinguish between the possibilities. Cosmologist Katie Mack has explored this scenario in detail. She points out that if vacuum decay occurred in the early universe, bubbles might have nucleated when the cosmos was tiny and densely packed. As the universe expanded through inflation and subsequent cosmic growth, these bubbles expanded too. Depending on when and where they formed, they could be anywhere now. If a bubble formed at a distance of 10 billion light-years from our location 10 billion years ago, it would arrive today. If it formed at 5 billion light-years, it arrived 5 billion years ago, and we're already inside it, though Earth wouldn't exist yet when it passed through. If it formed at 20 billion light-years, it won't arrive for another 10 billion years. The key question is, how common are bubble nucleation events? If they're extremely rare, the probability that any bubble formed at exactly the right distance to be threatening us now is negligible. If they're common, the universe might be filled with bubbles, and we'd expect to be surrounded by them. Current estimates suggest nucleation is extraordinarily rare, possibly only one event per Hubble volume, the observable universe, every 10 to the 140 years or longer. If that's accurate, the chance of a bubble threatening us is essentially zero. But these estimates depend on standard model physics and could be wrong by many orders of magnitude if unknown physics affects tunneling rates. There's also the question of eternal inflation. If the universe underwent exponential expansion in its earliest moments, creating vast regions of space far beyond our observable universe, then vacuum decay bubbles could be nucleating constantly in the infinite volume. Most would be too far away to ever reach us, but some might be close enough. In eternal inflation models, different regions of space experience different numbers of inflation cycles, creating a fractal structure of expanding space with occasional bubble nucleations. We might live in a relatively calm region where nucleation is rare, but surrounding us at vast distances could be regions where bubbles are common. We simply can't observe these distant regions, so we can't assess the threat. Another troubling scenario, maybe vacuum decay has occurred and we're inside a bubble right now, but we don't realize it because the transition happened so long ago that all evidence has been erased. Perhaps the false vacuum we think we're in is actually a true vacuum that we transitioned to billions of years ago. The physics we observe and call normal is actually the transformed physics. This seems less likely because our vacuum appears metastable based on current calculations. If we're in a true vacuum, it should appear stable, not metastable. But our calculations could be wrong, or there might be an even lower energy state that we haven't identified, making our true vacuum actually a second false vacuum. The philosophical implications are dizzying. We might be surrounded by approaching bubbles, or inside a bubble, or in a false vacuum that will decay, or in a stable vacuum that never decays. Each scenario feels different emotionally, but practically they're equivalent. We can't distinguish them, can't prevent any of them, and must live with the uncertainty. String theory and eternal inflation together suggest a multiverse, countless bubble universes, each with different physical laws, most causally disconnected from each other, together comprising reality at its largest scale. Vacuum decay fits naturally into this multiverse framework, but with disturbing implications. In eternal inflation, space is constantly expanding exponentially in some regions, while transitioning to non-inflationary phases in others, creating bubble universes like ours. These bubbles are true vacuum regions in the inflaton field's landscape. Our universe is one such bubble, having transitioned from inflating false vacuum to non-inflating true vacuum about 13.8 billion years ago. But the Higgs field has its own vacuum landscape, independent of the inflaton field. So our universe, itself a bubble in the inflaton landscape, might be metastable in the Higgs landscape. We're a bubble that could spawn sub-bubbles through Higgs vacuum decay. This creates a hierarchical structure. The eternal inflating megaverse contains inflaton bubbles, universes like ours. Each universe might contain Higgs bubbles, vacuum decay regions. Each Higgs bubble might itself be metastable to even lower energy states, creating sub-bubbles. It's bubbles all the way down, a nested fractal structure of different vacuum states. In this picture, vacuum decay is not a catastrophe, but a creative process, how the multiverse explores its possibilities, how different physical laws get instantiated, how cosmic diversity emerges. Our false vacuum is temporary, but it's part of something eternal and much larger. The multiverse interpretation provides cold comfort. Yes, reality as a whole survives vacuum decay. Yes, other bubbles with observers continue to exist, but we don't. Our bubble gets destroyed or transformed, and while other versions of us might exist in other bubbles, they're not continuous with us. It's not survival, it's replacement. Moreover, the multiverse raises anthropic questions. If countless bubbles exist with different physics, we necessarily find ourselves in one where the physics permits observers. This explains fine-tuning. We can't observe a universe incompatible with our existence, but it also suggests we should be typical observers in typical observer-permitting universes. Are we typical? Our vacuum appears metastable, right at the boundary between stability and instability. Is this typical for observer-permitting vacua? If so, why? Perhaps most stable vacua have physics incompatible with life, too few particles, forces too weak, etc., while most unstable vacua decay before life evolves. Only metastable vacua last long enough for observers while maintaining complex enough physics. If this anthropic reasoning is correct, we should expect to be in a metastable vacuum, which we are, but we should also expect decay to occur relatively soon on cosmic timescales, perhaps within the next few billion years rather than 1 to the power of 140. The fact that calculations suggest much longer timescales might indicate our models are wrong, or that we're anthropically selected to be early in the metastable period. This is all highly speculative. The multiverse hypothesis itself remains controversial, lacking direct empirical evidence, and possibly being untestable in principle. But if eternal inflation and string theory are correct, the multiverse is real, and vacuum decay is a ubiquitous feature of cosmic evolution. Vacuum decay leads us to philosophy's deepest question. Why does anything exist at all? Why is there something rather than nothing? And if our vacuum is metastable and will eventually decay, is nothing the universe's ultimate destiny? The traditional answer is that nothing is unstable. Even absolute nothingness would quantum fluctuate into something. In quantum field theory, the vacuum isn't nothing, but a seething foam of virtual particles constantly appearing and disappearing. Empty space is actually full of activity, full of potential. Perhaps reality exists because non-existence is impossible or unstable. But vacuum decay challenges this. if false vacuum transitions to true vacuum, and true vacuum has lower energy, and this process continues through multiple transitions until reaching the absolute lowest energy state, what is that final state? Is it genuinely nothing? No fields, no particles, no space, no time? Or is it still something, just something simpler and less structured than what we experience? String theory suggests the landscape has a lowest energy state, though identifying it precisely is difficult. This ground state might be completely empty, no matter, no radiation, no quantum fluctuations, just the barest possible existence. Or it might have some minimal structure, some residual fields or geometric properties that can't be eliminated without ceasing to exist entirely. The question becomes, does the ground state qualify as nothing? If it still has geometry, still occupies space and time, still allows quantum fields to exist even at minimal excitation, then it's not truly nothing. It's the simplest possible something, but something nonetheless. Perhaps true nothingness, absolute non-existence, is impossible. Perhaps existence is necessary, but the form it takes varies. Our structured, complex, life-permitting universe is one form. The ground state, after all vacuum transitions, is another form. Neither is nothing, just different degrees of somethingness. Or perhaps, and this is the darkest possibility, vacuum decay really does lead to nothing. The final transition, when the absolute ground state is reached, involves not just changing physics, but ending physics. Space and time themselves cease, fields vanish, existence terminates. The universe doesn't become simpler, it stops being. We can't know which scenario is correct without a complete theory of quantum gravity and a full mapping of the vacuum landscape. We're asking questions at the boundaries of physics, possibly beyond what science can answer. Whether existence is necessary or contingent, whether nothingness is possible or impossible, whether the universe has an ultimate fate or infinite transformation, these might be undecidable questions. But they're questions vacuum decay forces us to confront. Most physics describes how things change, not whether they exist. Vacuum decay touches the boundary between being and non-being, between existence and its alternatives. It reminds us that the universe's existence isn't guaranteed, that the laws we observe are temporary, that reality might be a temporary fluctuation in a more fundamental emptiness. Or perhaps it's the opposite, that emptiness is the temporary state, that existence is the natural condition, and vacuum decay is just transformation from one form of existence to another. We don't know. We're pattern-recognizing apes on a small planet, asking questions about the nature of reality itself. It's remarkable we can ask these questions at all. Whether we can answer them remains to be seen. We began with a simple observation from quantum field theory. The vacuum might be metastable. That observation led us through particle physics, cosmology, quantum mechanics, and philosophy, revealing that our entire existence, not just human civilization, but all structure in the universe, might be temporary in a profound sense. The evidence we've examined shows that vacuum decay is real physics, not science fiction. Precision measurements of the Higgs boson and top quark place us firmly in a metastable configuration. Calculations rooted in well-established theories give lifetime estimates that are reassuringly long, but not infinite. The possibility of catastrophic transformation is built into the foundations of reality. We've explored what vacuum decay would mean, an expanding bubble of true vacuum traveling at light speed, transforming all matter in its path, rewriting physical laws, creating a universe inside the bubble utterly alien to beings like us. We've examined whether it could be detected, prevented, or survived. The answers are probably not, almost certainly not, and definitely not. Yet we've also seen that vacuum decay forces engagement with deeper questions. Why do the physical constants have the values they do? How does consciousness relate to physics? What gives life meaning in a universe that might end at any moment? Can science answer questions about existence itself? Current scientific consensus accepts vacuum metastability while emphasizing the extraordinary timescales involved. The half-life of our vacuum is estimated at 10 to the 140 years or longer, incomprehensibly vast compared to the universe's current 13.8 billion-year age. For practical purposes, vacuum decay poses no threat during any timescale relevant to humanity, Earth, or even our galaxy's existence. But the possibility remains, and possibility is what haunts us. Quantum mechanics is inherently probabilistic. Low probability doesn't mean impossible, and when the consequence is infinite, the complete transformation or destruction of everything, even infinitesimal probability, carries weight. Perhaps the most profound impact of vacuum decay isn't the physical threat, but the philosophical challenge. It reveals that reality is more fragile, more contingent, more mysterious than our everyday experience suggests. The solid, stable, law-governed universe we perceive is actually a metastable quantum state that could spontaneously transition at any moment. This knowledge should inspire both humility and wonder. Humility because it shows limits to human power and understanding. We've discovered a threat we can't prevent, calculated probabilities for events we can't predict, and asked questions we might never answer. Wonder because the universe is stranger and more intricate than we imagined. Quantum fields permeate space, vacuum seethes with energy, and the laws of physics themselves might be temporary. How should we live knowing about vacuum decay? The same way we should live knowing about our own mortality, with awareness but not paralysis, with wisdom but not despair. Vacuum decay is cosmically more significant than individual death, but the existential questions are similar. If nothing is permanent, what matters? If everything can end, how should we choose? The answers come from philosophy, not physics. We create meaning through authentic choices and relationships. We value beauty, knowledge, and love not because they're eternal, but because they're meaningful now. We pursue understanding not to achieve power over nature, but to participate in something larger than ourselves, the universe examining itself. Vacuum decay reminds us we're part of a cosmos that existed before us, will likely exist after us in some form, and follows principles that transcend human concerns. Physics is how we connect with that larger reality, how we briefly touch the eternal, even knowing our touch is temporary. The universe is vast, ancient, and stranger than we comprehend. It might be metastable, poised between states, capable of catastrophic transformation. Or it might be more stable than calculations suggest. Or it might be part of an infinite multiverse where vacuum decay is commonplace, but survival continues in other bubbles. We don't know with certainty. What we know is this: we exist now, in this moment, in this remarkable universe where matter organizes itself into stars and planets and living beings and consciousness. That existence is precious precisely because it's fragile, meaningful precisely because it's temporary. Whether the vacuum decays tomorrow or in 10 to the 140 years, the fact that we're here at all is extraordinary. The bubble of death might be expanding toward us at light speed, or it might never form. Either way, we have this moment, this life, this chance to understand and experience reality. That's enough. It has to be.